Welcome back, students. In this video segment, we will cover two sections, sections 11.8, power series, and 11.9, representations of functions as power series. Now, before we get started, I want to mention a few things. First, you'll notice things are a little different in the beginning of this video as they were in previous videos. We have materials already written. The reason for that is my computer crashed when I recorded this lecture the first time, but the materials stayed on Notepad, so I lost the video, but my notes on my Notepad stayed. So we're going to use the notes that I had already written for the video that was lost when my computer crashed. So the second thing, and this is more to our course now, the second thing is these two sections represent, actually this lecture represents the most important lecture for our whole semester. The most important topic for the semester is series, and in series, the most important thing is this thing called a power series. Most important thing meaning for STEM majors, for science majors. So without further ado, let's go ahead and get started in this section. In section 11.8, we talk about something called power series. Well, before we dig into the concept of a power series, I want to rename the series, the types of series that we've been talking about so far. So far, the way we've referred to our series is just by calling them series. But now I'm going to add a little bit to their name. I'm going to refer to the series that we've talked about so far as series of constants, as opposed to what? Well, as opposed to something we're going to define as a power series in just a couple of minutes. So an example of a series of constants is the first series that you see listed there on your screen, the series 1/2 to the sum of 1/2 to the n minus 1. I think this is the first series we ever talked about in the course, and way back in section 11.2. If you write out the first few terms of the series, we get, when n equals 1, we get 1/2. When n equals 2, when n equals 1, we get 1. And when n equals 2, we have 1/2 to the 2 minus 1, which is 1/2. Then plus 1/4, plus 1/8, etc. This series is a geometric series, a convergent geometric series, and converges to 1 over 1 minus 1/2. The reason is reviewed for us right below on the next line. We notice that in red we have a general geometric series. General geometric series looks like the sum of a r to the n minus 1. And that series converges to a over 1 minus r if the absolute value of r is less than 1. This is old news for us. So back up to our original series that I have written. That should converge to 1 over 1 minus 1/2 because r equals 1/2 and a equals 1. So let's look at a few more of these things we're going to refer to now as series of constants. Notice that the things that we're adding up, the 1, 1/2, 1/4, 1/8, etc., those are constants. So that's why we're referring to these as series of constants. The next series of constants would be, instead of 1/2 to the sum of 1/2 to the n minus 1, let's say 1/3 to the n minus 1. Again, this is a convergent series. It converges to a over 1 minus r. A is 1, the first term, and r is 1/3. The next series, 3/7, the sum 3/7 to the n minus 1. A equals 1, r equals 3/7. And still one more. The sum 0.4 to the n minus 1, and it goes from 1 to infinity. The first term is 1, and r equals 0.4. Well, notice that the four series that we've looked at so far, 4 series that we've looked at so far are essentially series of exactly the same type. They're geometric series with A, the first term being 1, and R changing. So let's take the 1/2, the 1/3, and the 3/7 and the 0.4 out, and let's handle every possible series of this form. Let's put a variable x into the series. Okay, so now we're looking at the sum x to the n minus 1. There's no difference here in writing x instead of the specific constants 1/2, 1/3, 3/7 or 0.4. All I'm doing is saying, let's just look at every possible series of this form. So let's replace the individual constants with x. And what we get is, instead of 1 plus 1/2 plus 1/4, etc., we get 1 plus x squared plus x to the third, x to the fourth. This is nothing more than the series that we looked at in the red general power series right above. But instead of using r for the general value for r, we're putting in r equals x and a equals 1. And this series then converges to 1 over 1 minus x, as long as the absolute value of r, which is x in this case, the absolute value of x is less than 1. If we do this, if we put x in the series and get that series converges to 1 over 1 minus x, then what we've done is we've created something called a power series. A power series is different from a series of constants in that the constant, so to speak, is now variable. So if we look at this a little more critically again, then that says that 1 over 1 minus x is equal to the sum x to the n minus 1 for x, absolute value of x is less than 1. Now look at what this is saying. Look at this from the point of view of say, a pre-calculus course. In pre-calculus, we look at the function 1 over 1 minus x. And what this is saying is that simple function 1 over 1 minus x can be written as the sum of x to the n minus 1 for absolute value of x is less than 1. I've rewritten a simple function 1 over 1 minus x as a power series, as the sum of an infinite number of powers of x. And that's the whole idea with this section and the next one coming up. In fact, for the rest of our semester, for sections 11.8 through 11.11, the idea is to take common functions that occur in the sciences, in particular this one 1 over 1 minus x, but they could be functions like sine of x, cosine of x, e to the x, log of 1 plus x, etc. Take common functions that occur in the sciences and replace them with power series, with sums of powers. Why? Why would that be the most important thing we could do this semester? Well, most of that's going to be revealed in the next couple of hours, but to sort of give you an idea of why that's so important is in the sciences, we want to evaluate our functions at particular x values. We want to compute things like the sine of 5 or e to the 0.4 or the log of 1.7. And the power series allows us to do that. If, for example, in the power series that I have on the screen, we replace x with pi, then we can't, because the absolute value of pi is not less than 1, so that wouldn't work. Well, if we replace x with, let's say, 0.04, then 1 over 1 minus 0.04 then is equal to the sum, n goes from 1 to infinity, of 0.04 raised to the n. And why is that so important? Because the sum of 0.04 to the n is just using operations of addition, because the sum, multiplication, 0.04 raised to the n is just repeated multiplication of 0.04, and those operations are 2 of the 4 operations that our machines, our calculators and computers are able to handle. Our computers are able to handle addition, subtraction, multiplication, and addition. Addition, subtraction, multiplication, and addition. And division. I think I said addition twice. And power series involve only those 4 operations. So if I can consider even a more complicated example, if I want the sine of 0.7, that's a complicated quantity. But if I can represent the sine function as a power series, then the sine of 0.7 is replaced with an infinite number of additions, subtractions, multiplication, divisions, those things that our computers can handle. If this is unclear, we will clarify this concept more and more as we go through power series in the next hour and a half or so. Okay, so let's take a look at what power series are representing geometrically. So you're looking at a graph, and it looks like there's a lot of complicated things on that graph. So I want you to focus on just little bits of what you see on the graph at a time. First of all, notice that there's the black graph, the graph that's in black. That black graph is 1 over 1 minus x. Ignore the red parabola, the green horizontal line, and the yellow the other line. Just focus on the graph of y equals 1 over 1 minus x. So really briefly off to the side there, the graph of 1 over 1 minus x is this graph. Okay. Now, what I want to do is I want to estimate this function by using more and more terms of its power series. So now focus on the left-hand side of your screen. I have in green that 1 over 1 minus x is then approximately equal to 1. And that's what I get by using only one term in the power series. Remember what we did with alternating series is we estimated alternating series by using a certain number of terms of the infinite series. And then we introduce error. So we're doing the same thing here. Suppose we only use one term of the power series, and that says 1 over 1 minus x is then approximately equal to 1. Well, that approximation is not very good. Now look at the graph of y equals 1. Y equals 1 and y equals 1 minus x, the black graph, as long as x is just at 0, they coincide exactly. But as soon as we stray away from 0, either slightly to the right of 0 or slightly to the left of 0, the approximation gets pretty bad. Y equals 1 stays horizontal, but the curve y equals 1 over 1 minus x strays away from that. So a better approximation would be by taking that horizontal green line and tilting it up toward the curve. And we do that by taking another term in the power series. So now focus on the next line. You have then in yellow 1 over 1 minus x then is approximately equal to 1 plus x. 1 plus x is the graph of that line. Happens to be the tangent line, but it's the graph of that line. That graph of that line in yellow is the first two terms of the power series. And it's a better approximation to the function 1 over 1 minus x. We've reduced the error by tilting the graph up toward the curve. Well, how could we reduce the error even more? We could take the yellow graph and bend it toward the function, bend it upward. And we do that by taking another term in the power series, by looking at the green approximation, or the red approximation. 1 over 1 minus x then, by adding an additional term of the power series, is approximately 1 plus x squared. That's a parabola that bends if you will, the yellow line up toward the curve. So the more terms we take in the power series, the more these approximating polynomials, the approximating terms in the power series tend to wrap themselves around the function. If I wanted an extremely good approximation to this curve, I might let, in the power series, I might cut off at say the first 100,000 terms. Then you would get an approximating graph or polynomial that comes really, really, really close to the actual black curve, y equals 1 over 1 minus x. Okay. Also important to notice is that these approximating polynomials, the green 1 or the yellow 1 plus x or the red 1 plus x squared, these approximations are only good, they're only valid in the interval where the original power series converges. The original power series converges in the interval only between -1 and 1. Focus on the absolute value of x is less than 1. Okay, this is an interval that's centered about the origin and lies between x's -1 and 1. I'm going to graph that interval on our graph. So on our actual graph, I'm going to graph the interval, which I have in blue above, between -1 and 1. So I'm putting circles around -1 and +1, and I'm shading in along the x-axis the x values that we can put into our power series and have that power series converge to the actual function. So any of these approximations have to have x only picked from that interval where the function converges. For this reason, the power series for 1 over 1 minus x is said to be centered at x equals 0. Is said to be centered at x equals 0 because the approximation is only good for this interval where the original power series converged, and that was centered about an interval centered between -1 and centered about x equals 0. So for that reason, when our power series looks like powers of x squared, x cubed, x fourth, etc., we say that we're looking at a power series centered at 0. Okay, so the most general power series centered at 0 would look just like the one we have above, except the coefficients of the x's don't have to be 1. In fact, as we change the coefficients of the x's in our power series, we get different functions. Our whole thrust, or almost the entire thrust of this lecture, the most important lecture of your semester and of the next one, is how to find those coefficients for different functions. Okay, so the most general power series looks like the sum of c sub n, focus on what's at the bottom of the page or the screen, the sum of c sub n, x to the n runs from 0 to infinity. Notice that the sum goes from 0 to infinity instead of 1 to infinity. This is just arbitrary. It's standard to have our power series starting at n equals 0. And we'll talk more about that in a few minutes. That's not such a big deal. Okay, so our power series doesn't look like c sub n x to the n, where n starts from 0 goes to infinity. It looks like n goes from 1 to infinity, x to the n minus 1. It's exactly the same. It represents exactly the same type thing. This is, in fact, a power series, even though it's starting at 1 and not at 0. So power series, generally, the general power series we accept is starting at n equals 0, but the starting point's not important. We'd like our power series to be in terms of the sum c sub n x to the n. So I'm going to try to make our power series, the one we just looked at, the one for 1 over 1 minus x, I'm going to try to make it look like the n goes from 0 to infinity c sub n x to the n. And I'm going to do that by focus right now on the written out version, 1 plus x squared plus x cubed, etc., etc. 1 plus x to the 1 plus x to the second plus x to the third. In fact, you can think about that first term as x to the 0 plus x to the 1 plus x squared plus x. I can write this in a new form with sigma notation. What I'd like to have happen is when n equals 0, I get x to the 0. When n equals 1, I get x to the 1. I'd like to rewrite our series so that this happens. When n equals 2, I get x squared. When n equals 3, I get x cubed. So that should work out to the sum then as n ranges between 0 and infinity. Oops, I don't want to go too far. And goes from 0 to infinity of x to the n. Now check it out. Just to take the sum that I have written there, n goes from 0 to infinity, x to the n. Let n equal 0. If n equals 0, I get x to the 0 or 1. N equals 1, I get x to the 1, to the first rank. N equals 2, I get x squared, etc. So I've rewritten my power series that used to be in the form n goes from 1 to infinity, the sum of x to n minus 1, as a power of x to the n instead. Now notice that I can always do that. Notice what I did is I replaced n minus 1 with one bigger than that, with x to the n in the general term. And then I went to the index and did the opposite. I made that x equals 1 smaller. So if you replace the variable in the general term by a variable 1 bigger or 2 bigger or 3 bigger, then you adjust the starting point of this series in the opposite direction. You make it 1 smaller, 2 smaller, 3 smaller. And that's what I said saying on the next line. Notice that in my original power series, n started at 1 and went to infinity. But it was of x to the n minus 1. And I want to replace that with x to the n. So I made n minus 1 bigger by 1. So I start my series smaller by 1. So this is a skill, and it's a very easy one to master, that's going to be very important in section 11.9 to adjust our notation to accommodate our problems and stuff. So suppose I look at, before we dig into more of this section, suppose I look into perhaps the sum n ranging from 7 to infinity of x to the n minus 2. I'm sorry, I keep getting that stuff on the screen. Okay. Suppose I want to write it as a sum of x to the n. So I'm going to make n minus 2 bigger. N minus 2 plus 2 would be x to the n. So I'm going to make the starting point 2 smaller. So instead of starting at 7, I'm going to start at 5. And this adjustment, kind of an adjustment, can always be made. So there is a most important power series. And let's be real dramatic here. There is a most important power series in the universe. This is an exaggeration, but I'm going to use this exaggeration. And that is the first power series that we looked at today. The geometric series rewritten as 1 over 1 minus x equals the sum n goes from 0 to infinity, x to the n. You want to memorize that. This is the most important power series in the whole universe. And it converges for the absolute value of x less than 1. And we're going to be unfolding the reason why this is true as we go along. So, power series centered at 0 are always going to look like sums of powers of x to the n. And the reason we call them, again, power series centered at 0 is because they tend to converge in an interval surrounding 0, centered at 0. So in our case, the interval is between -1 and 1. Occasionally, not often in our course, but occasionally it's important to consider power series centered somewhere else than 0. Power series that converge, say, in an interval centered about some point x equals a. And what we get, or a generalization of what we're talking about here, we get things called power series centered at x equals a. And this is no big addition to our world right now. Imagine taking the power series C sub n x to the n. Imagine taking the power series that we've been talking about so far, C sub n x to the n. N goes from 0 to infinity, and shifting it, if you will, to the right by x equals a. Okay, so if our power series looked like powers of x to the n, remember from pre-calc to shift a function to the right by a, we replace x with x minus a. And that's all that's going on to consider the most general power series centered at a. We take x and replace by x minus a. So our power series, if you write it out, still looks like powers, but instead of powers of x, it's powers of x minus a. So when n equals 0, I get a constant. N equals 1, I get c1 x minus a to the first, and then plus c2 x minus a squared, etc., 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 etc. Okay. Okay. So for us, power series, the power series we generally consider, or most often consider, are going to be centered at 0. So we're going to be looking at sums that look like c sub n, sum of c sub n x to the power n, rather than x minus 3 to the n, or x plus 5 to the n, etc. Okay. What I'd like to focus on now for a little while is figuring out those values of x that I can put into a power series and have the power series converge. Remember, anytime we consider a series, whether it's a series of constants or a series of powers or whatever, we have the issue of convergence, that issue that you spend a lot of time on studying. So I'd like to consider a method for determining the values of x for which a power series converges. So let's take a look at an example. For what values of x do the following power series converge? Okay, so let's take a look at an example. Suppose we want to look at the power series where the coefficients c sub n are n factorial, or is n factorial. C sub n equals n factorial. Okay, and notice I have the power series starting at 0. 0 factorial is defined to be 1. Okay, it may not seem logical, but 0 factorial is defined to be 1. Of course, 1 factorial is also 1, but 0 factorial is 1. Why? You may not like the answer. Because we say so. And why do we say so? Because it makes mathematics work out for series. What we do, we just define 0 factorial to equal 1 so that the mathematics involving the factorial works out real nicely. So it's not a real gratifying answer, but that's the answer nonetheless. So what I'm going to do is, first of all, notice that that's not a series of constants. This is a power series. If you write that power series out, you get 0 factorial plus 1 factorial times x. That's a variable, x to the 1, plus 2 factorial x squared plus 3 factorial x cubed, etc., etc., etc. If I put in different values of x, I'm going to get different series that may or may not converge. So I'm going to use the mother of all tests to test this series for convergence. Again, that's kind of an exaggeration, but it's a powerful one. It's a real powerful thing to visualize, is that the ratio test has been really, really good to us. So I'm going to use the ratio test. The ratio test says, find the limit as n approaches infinity of a sub n plus 1 over a sub n. So I'm going to go through it. I'm going to find the quotient a sub n over n plus 1, take the absolute value, and evaluate that limit. So replace n with n plus 1. You have n plus 1 factorial x to the n plus 1 divided by a sub n, which is n factorial x to the n, and then do some algebra with that. Well, n plus 1 factorial is n plus 1 times n factorial. X to the n plus 1 is x to the n times x to the first. and divide by n factorial x to the n, and notice that I've already got canceled out for us. The n factorials cancel as factors, and the x to the n's cancel. So we're left with the absolute value on x and n plus 1 is not necessary because n plus 1 is positive, but x is not necessarily positive. X is that variable that goes into our series, so we keep the absolutes on that. What is that limit? Well, x doesn't depend on n, so this limit does not, evaluating this limit doesn't involve x. So what we can do is we can factor out the absolute value of x and then continue with the limit. We can factor out the absolute value of x and write this as the absolute value of x times the limit as n approaches infinity of n plus 1. Sorry about the phone there, folks. Oh, yeah, sorry about my writing too. Let me clean that up a little bit. This looks terrible. So we're looking at the limit at the absolute value of x times the limit as x approaches infinity of n plus 1. Okay. Well, without that absolute, just cover up the absolute value of x, either mentally or with your finger, and with the limit of n plus 1, that's infinity. And if the ratio, by the ratio test, that means that the series diverges. And that limit is infinity as long as you don't choose x equals 0. If you choose x equals 0, the limit is 0. Because 0 times anything is 0. But if you choose anything else for x, like x equals 1/2, you have the absolute value of 1/2, which is 1/2 times infinity. And infinity is more than 1. So if x equals 0, we have convergence because the ratio test says that since 0 is less than 1, we have convergence. If x is not 0, we get infinity, which is more than 1. We get divergence. Here, I've sort of summarized that in the next line. If I choose x to not equal 0, I'm going to get an infinite limit. And infinity is more than 1, so I get divergence of the series if I don't put in x equals 0. But if I do put in x equals 0, I get this quotient, absolute an plus 1 over an going to 0, which is less than 1. I get convergence. So the series converges only if x equals 0 and diverges otherwise. So the answer is, the question was, what values of x can I put in for convergence? Only 1. The series is not very exciting, and most of our series will not just converge at 1 point. But that is true about our particular series. Our series converges only if x equals 0. Okay. All right. So let's consider another example. Let's consider the sum x to the n. Well, that was our original power series that we looked at. We know this converges for the absolute value of x less than 1. So for us, this is a quick one. This was the original series we looked at, and since it was geometric, it converged for absolute r, but r is equal to x. Absolute value of r is less than 1. That means that the series converged in an interval between -1 and 1. This interval's centered at x equals 0, but not including the endpoints. Okay, so let's take a look at another one. The previous series was the sum of x to the n. Now let's make those terms really small, real fast. Let's divide x to the n by n factorial. N factorial gets big real fast. So let's use a ratio test on that. Let's take the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. Then let's substitute a sub n plus 1. X to the n plus 1 over n plus 1 factorial. And let's substitute a sub n. And let's divide those things. So we're going to invert and multiply and use a bunch of algebra. So x to the n plus 1 is still x to the n times x to the 1. N plus 1 factorial is n plus 1 times n factorial. Inverting and multiplying x to the n over n factorial becomes times n factorial over x to the n. Cancel out some stuff. N factorials cancel. X to the n's cancel. And we get the absolute value of x over n plus 1 as n approaches infinity. Once again, that absolute value can factor out of the limit. The limit doesn't depend on x, it depends only on n. And look at that limit on the right-hand side, the limit of 1 over n plus 1. N plus 1 goes to infinity, so 1 over n plus 1 approaches 0. This limit is 0. The absolute value of x times 0, which is 0. And 0 is less than 1, no matter what we put in for x. If I put in x equals a billion, the absolute value of a billion times 0 is still 0. So this series converges for all x. It's still an interval centered at 0, but it's everything. It's the whole x-axis. Okay, so let's take a look at another series. Let's make the denominators big again, but not so big as before. In the previous example, the denominators were n factorial. N factorial gets real big real fast. Let's just divide by something that gets big sort of really moderately slowly. Let's look at dividing by n, x to the n over n. Let's use the ratio test again. So we're going to compute the limit as n approaches infinity of a sub n plus 1 over a sub n in absolute value. Okay, if we substitute n plus 1, we get x to the n plus 1 over n plus 1. No factorials this time. And then divide by a sub n, x to the n over n. And if we invert and multiply, a little algebra on x to the n plus 1, the x to the n's cancel. We get the limit of n over n plus 1 times the absolute value of x. So what happens with this limit? The absolute value of x can come out of there, and the limit of n plus 1 over n over n plus 1 is just 1. So the limit of the a sub n plus 1 over a sub n in absolute value goes to the absolute value of x. And what we do is we set this less than 1 for convergence. For the ratio test says that that ratio needs to be less than 1 for convergence. Okay, well, that means x is between -1 and 1. But we're not out of the woods yet. You see, the ratio test gave us no information when the limit was equal to 1. So we have to check separately the endpoints of our interval. The endpoints of our interval correspond to when the ratio test provides an answer of 1 for the limit. So we've got to check the endpoint. We have no information from the ratio test about what happens at -1 and 1. So let's check those points separately. Let's check x equals -1. Now our original power series is the sum x to the n, the sum of x to the n over n. Okay? Don't forget that our original power series is, and I've highlighted it in red for us, it's the sum x to the n over n. So substitute x equals -1. So I'm looking at -1 to the n over n, substituting x equals -1. That I can rewrite in our familiar form for an alternating series. Use the alternating series test on that. 1 over n is decreasing. What does the second part say for the alternating series test? It says that we need 1 over n to approach 0. It is. So that series converges. So at x equals -1, the series converges by the alternating series test. Well, let's try the other endpoint, x equals 1. So we have the sum 1 to the n over n. 1 to the n is just 1. What does that series do? This should be automatic for you. This is the sum of 1 over n. That is just the harmonic series, or p series, with p equals 1. So that series diverges. So something a little strange is happening that didn't happen before. We're getting convergence at the left-hand endpoint and divergence at the right-hand endpoint. So the answer is that this series converges in the interval from -1 to 1. These intervals where our series it converges, the values we can put into our series for convergence, those are called the interval of convergence for a power series. A power series centered at x equals 0 will always converge in some interval centered about 0. Always, and diverge everywhere else. Okay, so I want to look at that fact. This is a very important fact. The original series that we looked at in this example was n factorial to some x and n factorial x to the n. It converged only at 0, and I graphed it on the x-axis. That's a real tiny interval centered about x equals 0. It has only 1 point. The next series, x to the n, converged in an open interval about x equals 0, not including the endpoints. The next one converged in a huge open interval centered about 0, the whole x-axis. But still, it's convergence in an interval centered at 0. The interval of convergence for every power series centered at 0 must be in an interval centered at 0. I'm going to summarize that in a minute. The last one that we just looked at was still convergence in an open interval, no, not an open interval, half open interval centered at 0, but it was still centered at 0, but we got convergence at one of the endpoints. These ideas generalize. Convergence of a power series centered at 0 always occurs in an interval centered at 0, whether it's at a single point everywhere, the whole x-axis, or in some interval of finite length centered at 0. That's how we summarize this concept of convergence of power series centered at 0. So given a general power series centered at 0, sum c sub n x to the n goes from 0 to infinity, then exactly one of the following must hold true. Either the series converges only at 0, the series converges for all x, for x between negative infinity and positive infinity, or, and this is a little complicated looking, but the idea is not so bad, the series converges for absolute value of x less than some real number r, diverges for absolute value of x more than that, and may do either at the endpoints. You see, the interval for the absolute value of x less than r, that's the interval from negative r to positive r. When x equals, absolute value of x equals r, that's the two endpoints, x equals actual negative r or positive r. We have to check those two endpoints separately. The first case one was just this is our third case. Our third case then says that the series can converge at either an open interval centered at 0 from negative r to r, half open interval from negative r to r, convergence at the left but divergence at the right. The opposite of that, convergence at negative r and divergence at negative r and convergence at positive r, or convergence at both endpoints. So the third conclusion really needs to be looked at the most. Most of the work is done with the third condition. If we find that our interval of convergence has finite length, we got to check the endpoints of convergence. So most of our series will be power series centered at 0. So for most of our series, we're going to be looking at convergence at an interval centered about 0. But remember, we can also have general power series converging at some converging in an interval surrounding x equals a. Okay, so if we shift the concepts, if you will, of the power series centered at 0 to the right by a, then we get the same conclusion. Either the power series centered at a converges at only one point, x equals a, for all real numbers. So a power series centered at x equals a, the interval centered at a is all real numbers. Or the trickiest one, the interval is, and the interval of convergence is some interval surrounding or centered at x equals a. So from a plus r to a minus r. That's a fancy way of saying the absolute value of x minus a is less than r. And then we would check the endpoints separately for convergence. Okay, that r, that distance from the center to the edge of our interval of convergence, that's called the radius of convergence. So power series centered at the so for example, if we have a power series, the sum c sub n x to the n centered at 0, and suppose that power series converges from -5 to +5, then the radius, the distance from the center of the interval of convergence x equals 0 to the edge, to either edge, -5 or +5, that distance is 5. So we call that the radius of convergence. Notice that the radius of convergence doesn't depend on whether we have the endpoints included or not. It's just the distance from the center of your interval, and power series centered at 0 will always have the center at x equals 0. So the center of the interval to either the edge on the right, 5 in the previous example, or edge on the left, -5. Okay, so that takes care of section 11.8. So now let's dig into the most important section. Now remember, I said that this lecture was the most important section for the whole course. In this lecture, the most important section is 11.9. So we're coming to, in this section, 11.9, the most important section for the entire course: representations of functions as power series. So let's dig in. Okay, so 11.9, representation of functions as power series. So why have power series at all? Why? Why would we have a power series 1 over 1 minus x equals 1 plus x squared plus x cubed plus x to the fourth, etc., equals the sum x to the n goes from 0 to infinity? Why would we take a function 1 over 1 minus x and rewrite it as a sum of powers in a restricted interval for x between -1 and 1? Well, the reason again is, in the sciences, we need to estimate functions, and lots of them, and our machines are able to do the 4 operations: addition and subtraction, multiplication and division. So the idea is to take something like 1 over 1 minus x and estimate it with a few terms of its power series. Generally, it's going to be more than 3 terms, but just for an example, 1 over 1 minus x then can be approximated by the quadratic polynomial 1 plus x squared. And the operations required on the right are very simple. They're just addition and multiplication. So for the almost all of this remaining section, we want to find power series representations for different functions. So let's start with, for example, find the power series for 1 over 1 plus x. And remember, as soon as we find a series, a power series, we have the issue of, well, where does that power series converge? What is the power series? What is the range of values, the interval of values for which that power series representation is valid? So let's do it. We have one most important power series in the universe, and that's the original power series, the sum for the power series for 1 over 1 minus x. And the idea in this section is going to be to recycle that power series, that one power series, to create a whole bunch of power series for power series for a whole bunch of other different functions. So 1 over 1 plus x. How can I use the original power series for that? I have the most important series in the world right now. 1 over 1 minus x is the sum of x to the n, going from 0 to infinity. So replace x with negative x in that function. If you replace x with negative x, I have 1 over 1 plus x equals 1 over 1 minus negative x, and then replace negative x in the power series. So I have that 1 over 1 plus x then is now, n goes from 0 to infinity, negative x to the n, and that converges for the absolute value of negative x. Everywhere I see an x in that most important power series, I'm replacing negative x for the absolute value of negative x less than 1, and then go forward with that. Well, negative x raised to the n is the same thing as negative 1 to the n, x to the n, and the absolute value of negative x is the absolute value of positive x. So that is our power series representation for this new function. Okay, that's it. That's the whole idea, is to find power series representations by recycling an easier one, an easier known power series. So just to emphasize what's going on here, we have our power series representation. 1 over 1 plus x is this alternating series. Write out a few terms. It's 1 minus x plus x squared minus x cubed plus x to the fourth, etc., etc., etc. This is our power series representation for this new function, 1 over 1 plus x. Okay, so let's do this for some other functions. So find a power series representation for each function and the interval of convergence. The interval of convergence. Okay, so for example, part A, the function is 1 over 5 plus x. 1 over 5 plus x. Okay, and don't ever lose track of the idea that we're trying to recycle over and over and over again, that 1 over 1 minus x equals the sum x to the n ranges from 0 to infinity, and this power series converges for the absolute value of x less than 1. This is what we have, and what we want is 1 over 5 plus x. Well, the 5 is a problem. So force the 5 not to be there anymore. So 1 over 5 plus x equals, factor out of 5 from the denominator. Well, that solves one problem and creates another one. If you factor out a 5 from the denominator, looking at 1/5 times 1 over 1 plus x over 5. And we got two problems there. The power series we have has minus, it's 1 over 1 minus x, and the power series we have doesn't have, the function we have for the power series is not 1, it doesn't have x over 5, it has x. So try to force our function to fit what we have. So this is 1/5 times 1 over, I want it to be minus, so make it minus. And then use our power series, the one for 1 over 1 minus x, and substitute negative x over 5 into the power series. So this becomes 1/5 times the sum, n ranges from 0 to infinity, of negative x over 5 to the n. Okay, and this power series converges for the absolute value. I'm replacing x with negative x over 5, so it's for the absolute value of x over 5 less than 1. Okay, and then simplify this new power series to look like a power series in powers of x. So I can rewrite this as 1/5 times the sum, n ranges from 0 to infinity, of negative x to the n over 5 to the n. Okay, and if I multiply both sides by 5 and eliminate the negative because of the absolute value, there's my interval of convergence. And rewrite this in the familiar form for a power series. N goes from 0 to infinity. Maybe bring in the 5 from the denominator and rewrite negative x to the n as negative 1 to the n x to the n. So this becomes negative 1 to the n over 5 to the n plus 1 times x to the n. And that's our power series for the absolute value of x less than 5. Okay, so we have a function 1 over 5 plus x, and its power series representation in a power series centered about 0 is that power series. And we haven't had to use any fancy formulas, just the one series, the one series that we have to begin with. The sum x to the n goes from 0 to infinity, is 1 over 1 minus x. Let's try another one. Part B. Part B. I want a power series representation for another function, 1 over 1 plus x squared. Okay, well, we have one power series that we want to recycle over and over again. It goes from 0 to infinity for the absolute value of x less than 1. So our function doesn't have 1 over 1 minus x. It doesn't even have 1 over 1 minus. It has 1 over 1 plus. And it doesn't have x. It has x squared. Not a problem. Take our function 1 over 1 plus x squared and rewrite it as 1 over 1 minus negative x squared. And replace in our given power series, the one we recycle over and over again, replace x with negative x squared. So negative x squared to the n for the absolute value of negative x squared is less than 1. And rewrite this. This is just the sum n goes from 0 to infinity, negative 1 to the n, x to the 2n, for the absolute value of x squared less than 1. The absolute value of negative 1 is positive 1, so the negative goes away. Take the square root of both sides in there, and you get that our power series representation is n equals 0 to infinity, negative 1 to the n, x to the 2n, for the absolute value. Taking the square root of both sides, absolute value of x less than 1. So what does that mean? 1 over 1 plus x squared. Let's write out a few terms. When n equals 0, I get 1. Negative 1 to the 0 is 1. X to the 0 is 1. When n equals 1, I get minus x squared. When n equals 2, I get plus x to the 4th. N equals 3, minus x to the 6th, plus x to the 8th, plus dot, dot, dot. As long as x is between negative 1 and 1. So for absolute value of x less than 1. So this power series represents, or rather our function 1 over 1 plus x squared is represented by this alternating power series that has only even powers. This may not seem amazing to you, but this really, a lot of the sciences are held together by our ability to represent functions as power series. Okay, so we need more. We have other functions that we need to represent by power series, and I would like to recycle our simple power series over and over again, but we need more tricks. The next trick is based on the idea that it's possible to use some calculus on the power series. We can differentiate power series. We can integrate power series, and that will not affect the radius of convergence of a power series. That's kind of a really big chunk to chew there. So let's take a look at what I'm talking about here. Okay. So let's assume that I want to take the derivative of a power series. So let's call this a theorem. If f of x equals c sub 0 plus c1x plus c2x squared plus c3x cubed. So f of x is given by some power series, or equivalently in sigma notation form, c sub n x to the n goes from 0 to infinity. Then we get two conclusions. Then a f prime of x is, and to get f prime of x, I can differentiate the terms in the power series term by term. So the derivative of c0, a constant, is 0. The derivative of c1x is c1. The derivative of c2x squared is 2c2x. The derivative of c3x cubed is 3c3x squared. So this theorem says that I can differentiate power series term by term. Okay, we don't have to look at the series written out term by term. We can simply take the derivative of the series in term by term in sigma notation form. So the derivative of c sub n x to the n is n c sub n x to the n minus 1, and n goes from 0 to infinity. Now I can make an adjustment to this, though, that may not be clear. All I did was I brought down the power in the sigma notation, decreased the power by 1. But this is better written as n goes from 1 to infinity, n cn x to the n minus 1. The only difference is I've written the last sum going from 1 to infinity instead of from 0 to infinity. Why? Well, look at the sum from 0 to infinity. When n equals 0, the coefficient of c sub n, which is n, is 0. So we lose the first term. That means I can, when I take a derivative of a power series, I shift the index of summation up by 1. That's no mystery. The first term in a power series is constant. And the first term in the power series was c sub 0. The derivative of c sub 0 is 0, so we lose a term. If we lose a term, we start then at n equals 1 instead of n equals 0. That's an important thing to notice. I'm going to highlight this thing. I'm rewriting what I just wrote. The derivative of the power series starts with the lower index of summation, 1 bigger than we started out, because the derivative of the first term is 0. Okay, that's important. Okay. The second conclusion is that we can integrate power series. That the integral of a power series, the integral of this function, is c, some constant of integration, plus the integral term by term of each of the terms in the power series. The original power series was c sub 0 plus c sub 1x plus c sub 2x squared. I'm going to put a green arrow to the original series. We'll integrate each term by term. The integral of c sub 0 is c sub 0x. The integral of c sub 1x is c sub 1 x squared over 2. c sub 1 x squared over 2 plus c sub 2 x cubed over 3 plus ... So I add a constant of integration plus the sum using sigma notation. N goes from 0 to infinity. We don't make any adjustment to the index when we integrate. The integral, the original function, look at in with the yellow arrow with sigma notation. The sum c sub n, x to the n. Integrate x to the n, you get x to the n plus 1 over n plus 1. So the integral is going to be c sub n, sum, n goes from 0 to infinity, c sub n, x to the n plus 1 over n plus 1. Okay. So this theorem also works for power series centered about A. So the only difference for a theorem centering your power series about x equals A is all the x's would be replaced with x minus A. Okay, seriously, the most important thing for us is what I have in red. The integration is also important, but the most important thing for us is this thing that's written in red, that's highlighted in red, that says that the derivative increases the index of summation by 1, and then just take the derivative of the general term. Okay. The something also that I mentioned but I didn't write out is the radius of convergence doesn't change. The radius of convergence remains the same. When we integrate or differentiate a power series, the radius of convergence remains the same. However, the endpoints of the interval of convergence must be rechecked. When you integrate or differentiate a power series, you keep the same interval of convergence almost, but you have to recheck the endpoints. You have to recheck the endpoints of the interval. Okay, so why would we differentiate or integrate a power series? The answer to that is right now. Example. Find a power series representation for each function. Okay, part A. I want a power series representation for 1 over 1 minus x squared. This is tricky. This is very tricky. It's extremely difficult to do this without using the idea that we can differentiate a power series. Okay, it's extremely difficult to do this without using derivatives. Now here's the trick. The trick is to notice that the derivative with respect to x of 1 over 1 minus x is, let's just use some Calc 1 to do this. It's the derivative with respect to x of 1 minus x to the negative 1, bring down the power, decrease the power by 1, chain rule, multiply by derivative inside. The derivative of 1 over 1 minus x is 1 over 1 minus x squared. Okay. I want to look at this formula I just wrote. Again, 1 over 1 minus x squared is the derivative with respect to x of 1 over 1 minus x. Okay. We just showed that. There's nothing new here. I just wrote 1 over 1 minus x squared first. Now, the main part of the trick then is to substitute into this formula on the right-hand side the power series that we know. 1 over 1 minus x 1 over 1 minus x is the sum x to the n runs goes from 0 to infinity. And the theorem that we just looked at says that I can take that differentiation operation, d over dx, inside the power series now. So this becomes the sum n x to the n minus 1 to infinity. But n now starts where? When you differentiate a power series, you move the lower index of summation up. Okay, so this is for absolute value of x less than 1. Okay, and I'm not going to check the endpoints for a convergence. I want to just get the power series representation. Now, for most of our work, we'd like our power series to be in terms of x to the n, not x to the n minus 1. So I'm going to use that trick we looked at in the last section. I want to have the power series as the sum of some coefficients x to the n, not x to the n minus 1. So I'm going to replace n, all the variable, I'm going to increase, let me say this again, I'm going to increase the variable in the general term by 1. I'm going to add 1 to everything. So instead of having n, I'm going to have n plus 1. Instead of having x to the n minus 1, I'm going to have x to the n. So I've increased by n, I've added 1 to the variable. So I'm going to decrease the index of summation by 1, by that same amount. Okay, and that is our power series for 1 over 1 minus x squared. If you write out a few terms, you can get an idea of what it looks like. When n equals 0, I have 1. When n equals 0, I have 1. When n equals 1, I have 1 plus 1 is 2, x to the 1. When n equals 2, I have 3x squared. When n equals 3, I have 4x cubed plus dot dot dot. That is our power series centered at 0 for 1 over 1 minus x squared. Okay, let's look at another one. I want a power series representation for the inverse tangent of x. Now that seems like a tall order. That seems like a very complicated thing to do. And I only have this to use. I only have that that 1 over 1 minus x. 1 over 1 minus x is the sum x to the n. N goes from 0 to infinity. That's all I got. Okay, for absolute value of x less than 1. Now I'm going to use a trick here. I'm going to use a trick again. We have that the integral of 1 over 1 plus x squared with respect to x is the inverse tangent of x plus a constant. This is an old standard for us. So what I'd like to do is I'd like to write this formula a little differently. I would like to write this formula as the inverse tangent of x equals, let's put the constant of integration on the other side. A constant of integration plus the integral of 1 over 1 plus x squared. My ones are getting really squiggly here. Hold on. Let's see if I can erase some of these terms. Okay, here we go. We have the inverse tangent of x equals a constant of integration 1 over 1 plus x squared. Now look under that integral sign and look way back to, where is it? Way back. I didn't realize it was out here. Part B of the previous example. In part B, we have an important series. in part B, we have the series 1 over 1 plus x squared. And I'm going to highlight that series because we're about to use it. We have that series, and well, if my Surface will let me highlight this, I'm going to highlight in red. We have a power series representation for 1 over 1 plus x squared. And we used our standard 1 over 1 minus x function to get it. So I'm going to use that series for 1 over 1 plus x squared. Is the sum, n goes from 0 to infinity, negative 1 to the n, x to the 2n, in my current example. It's going to be hard on your eyes here. So I'm going to replace, underneath the integral sign, the sum, negative 1 to the n, x to the 2n, n ranges from 0 to infinity, and I'm going to integrate that with respect to x. Now I'm going to pass the integral sign into the series, past anything that doesn't have an x in it, negative 1 to the n until it hits x to the 2n. That theorem that we said about the integration allows us to do that. So this is now c, a constant of integration, plus n goes from 0 to infinity, negative 1 to the n, x to the 2n, integrate 2n plus 1 over 2n plus 1. Okay, that's amazing. That says our inverse tangent function is this power series. The only thing missing is that we need to find that constant of integration. Inverse tangent doesn't have a constant in it. So I'm going to find that constant of integration. So I'm going to find c by letting x equal 0 on both sides. So I'm going to get the inverse tangent of 0 equals c plus the sum, n goes from 0 to infinity, of just negative 1 to the n times 0. It's just 0. So this says the inverse tangent of 0, which is 0, equals c plus the sum of a bunch of zeros is 0. The constant of integration is 0. This is amazing. This is the reason why series are so absolutely important. This is saying that my inverse tangent function is this power series. Let's write out a few terms of that series. This is saying the inverse tangent of x equals, when n equals 0, I have x. N equals 0, negative 1 to the 0 is 1. X to the 2n plus 1 is x to the 1 over 1. When n equals 1, I get minus x cubed over 3. N equals 1, I get 2n plus 1 is 3. N equals 2, I have x to the 5th over 5 minus x to the 7th over 7 plus dot dot dot. This is the power series expansion of the inverse tangent function. This is the power series expansion for the inverse tangent function. It contains all the, it's alternating, it contains all the odd powers of x. So what could this possibly be used to do? Suppose in our calculator I wanted to compute something like pi over 4. How does our calculator compute pi over 4? It isn't programmed with pi over 4 in the memory. It computes pi over 4. Well, look what happens when you let x equal 1 in your tangent, inverse tangent expansion. The inverse tangent of 1 is pi over 4. Now substitute it into the series. It's 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9, etc., etc. This is what pi over 4 equals. So how do we compute it? Well, we have an alternating series. We decide how much accuracy we want. We use the alternating series estimation theorem and stop at n equals 500 if we want 35 decimal places of accuracy or whatever. This is real-world computation. Now, to keep it real, I happen to know a little bit about this particular power series. It converges very slowly. So it takes a large number of terms to even get a few decimal places of pi over 4. So in reality, a faster converging power series would be used. But this is how real-world computation is done, okay? I'm going to end our lecture with a fairly complicated example because of the algebra, but it really illustrates the absolute importance of power series. This computation that I'm doing in this example is a real-world computation. A science major, engineering, physics, whatever, will have to compute integrals often, very often. Suppose I want to compute the integral of the inverse tangent of x squared from 0 to 1. 1/2 rather. Okay, so the example is to, I haven't put the directions here, so let me get some directions for this example. The example, our problem, is to estimate this integral, and only a few things moved. Give me a second here. I'll clean this up. Estimate the integral from 0 to 1/2. Estimate it. We've done this kind of stuff before. But before we use Simpson's rule, trapezoid rule, midpoint rule, and stuff. So we're doing something similar. In fact, we're doing exactly the same thing we did before, but we're going to do it using power series. Estimate this integral with the error, the magnitude of error, let's say the absolute value of the error, less than 10 to the negative 7, or 0.00000001. So say we want to estimate this integral with 6 decimal places of accuracy. And we're going to use power series to do this. We're going to use the power series for the inverse tangent to do this. Okay, so let's do it. The integral from 0 to 1/2, the inverse tangent of x squared with respect to x is, I'm going to use the power series for the inverse tangent of x, and I'm going to substitute x squared inside. So the inverse tangent of x, power series, is negative 1 to the n, x to the 2n plus 1 over 2n plus 1. And starts from 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1. But we're not finding the inverse tangent of x, we're finding the inverse tangent of x squared. So I'm going to substitute into that power series x squared. And we integrate that result with respect to x. And then continue. A whole bunch of algebra follows now. Okay. So this becomes the integral from 0 to 1/2 of the sum, n goes from 0 to infinity, negative 1 to the n. When we raise a power to a power, we multiply the power, so this becomes x to the 4n plus 2 over 2n plus 1. Integrate that with respect to x. I'm going to pass the integral sign into the summation past everything with n's in it and no x's until I hit something with x's in it. So I'm going to get the integral sign inside that sum. So this is n goes from 0 to infinity. Negative 1 to the n doesn't have any x's on it. 2n plus 1 doesn't have any x's on it. I stop when I hit x to the 4n plus 2. Integrate that with respect to x from 0 to 1/2. Okay. The integral is very simple. It's just a power, x to the 4n plus 2. So this becomes no strange techniques of integration, elaborate integration techniques are necessary. This is just powers. Negative 1 to the n over 2n plus 1. X to the 4n plus 2, increase the power by 1, so it's x to the 4n plus 3. Divide by that new number, 4n plus 3. X is carried between 0 and 1/2. Push forward. This becomes the sum. N goes from 0 to infinity. This is an alternating series. Negative 1 to the n. Substitute x equals 1/2. 0.5 to the 4n plus 3 over 2n plus 1. 4n plus 3. Look at that complicated series. That complicated series is the value of my integral. Now, what kind of series is this complicated series? And by that I don't mean is it a geometric series or a p-series. I mean, look at the negative 1 to the n term factor. That says this is an alternating series. I could use the alternating series estimation theorem on this to get a handle on error. I'm going to write out some terms of this series. This series, when n equals 0, I get 0.5 cubed over 3. When n equals 1, I get 0.5 to the 7th over 21. When n equals 2, I get 0.5 to the 11th. I did all these computations off camera. Over 55. I want to write out a few more terms. We're going to need them. The next term is 0.5 to the 15th over 105. One more term, plus 0.5 to the 19th over 171. And it continues for on and on and on and on and on and on, over and over and over, off to infinity. Okay. Now the thing is, again, this is an alternating series. I want my error to be less than 10 to the negative 7th power. The term 0.5 to the 15th over 105, just that number alone, that number equals about 2.9 times 10 to the negative 7. 2.9 times 10 to the negative 7 is greater than 10 to the negative 7. The next term, 0.5 to the 19th over 171, that number is about 1.1 times 10 to the negative 8th. That number is definitely less, that's much less than 10 to the negative 7th. So my alternating series estimation theorem says that I can add the terms up just before that. So by the alternating series estimation theorem, look back at our sum. Since that term, that 0.5 to the 19th over 171 is less than my error, That says I can cut my series off right there, and my integral will then be approximately the terms before that. And my error is definitely is guaranteed to be less than 10 to the negative 7th. Okay, those terms then add up to this. So our integral of the inverse tangent of x squared from 0 to 1/2 then approximately equals, and I added those terms up, 0.41303030054. The true value of the integral, the actual value of the integral is 0.0413032408. How is that by calculator? My calculator is programmed to give exact values of the integral to as many decimal places that show up. How much agreement does our estimate have to this? Well, let's take a look. Let me move this over just a little bit. Move this way just a little bit. This may not be effective. We'll see. It's okay. Probably should have left it. So we have agreement in our integral in our values up to this place right here. Okay. Our maximum error was guaranteed to be less than 10 to the negative 7th, or 0.12345 zeros and 1. That means we are guaranteed 1, 2, 3, 4, 5, 6 decimal places of accuracy. At least our error was less than that. We got 1, 2, 3, 4, 5, 6, 7 decimal places of accuracy. So our error estimate worked out just fine. This, my good students, is the most important aspect of the entire course. The ability to make real-life scientific computations using power series. This is the most important by a whole long way. By long ways, this is the most important aspect of Calculus 2. And with that, we end section 11.9. Okay, and I'm looking forward to talking with you all again soon.